Hello APC Mechanics students in Unit 5 Rotation, Class 2 5.1 Torque and Rotational Statics Part 2. In Section 1 Translation and Rotational Equation, consider an extended object of mass m acted by a set of forces, say for example 1, 2, 3 and 4. Translational equilibrium, the object is said to be in translational equilibrium if the forces are balanced forces, so which means that F naught is equal to 0, which give the birth to two linear equations, one along the horizontal and one along the vertical. Here we say that forces that are up balance the forces that are down, and left forces balance the right forces, which is a consequence of Newton's first law of inertia. Now, what about the rotational equilibrium? Because we know that the force has an analogy, which is the torque, so we can say torque net would be 0. Then let me say the object is said to be in a rotational equilibrium of the net torque of the applied forces about a certain pivot sum up to 0, which means torque net is equal to 0. Here what I'm trying to say is that since we agreed that the analogy of the force is the torque, so if Newton's first law is given by F net is equal to 0, which means that the analogy of that would be torque net is given by 0, which dictates the rotational equilibrium, which give the birth in this case to one linear equation. Now, the only difference between this one and this one is that this gives the birth to two linear equations, while this one, although it's a vector equation because torque is a vector, however, it will give only the birth of one linear equation. If an object is in equilibrium, then we have both translational equilibrium and rotational equilibrium. Then whenever we know that an object is in equilibrium, then we can use this condition, which is forces are balanced along the horizontal and the vertical, and the net torque about any pivot point of our choice would be 0. This is very important, right? As we shall see in exercise 1. A uniform bridge 24 meter long and weighing 5 times 10 to the power 5 newtons is supported by two pillars located 4 meters from each end. A 2 times 10 to the power 4 Newton car is parked 8 meters from the left end of the bridge. In part A, we need to calculate the force the left side pillar exerts on the bridge. So we need to determine the force Fp1. Now here in this case, what are the different forces that are acting on the system? We have two apparent forces, and we always have some hidden forces, like for example the pull of gravity. So we have the pull of gravity of the bridge and the pull of gravity of the car that are acting on the bridge. Now, because the bridge is uniform, then the pull of gravity of the bridge would be acting on the center of mass of the bridge itself due to the geometry of the figure, and the pull of gravity of the car would be acting on the bridge 8 meters as shown in the figure. Now here we suppose that the system is at equilibrium, then we can use both rotational and translational equilibrium. It's healthy to start with the translational equilibrium because it's more easier to deal with. Then let me say Fp1 plus Fp2, the forces that are acting up, should balance with the forces that are acting down, and that is the case. Here let me say one thing, that we don't have normal reaction because the bridge is not being supported by any pivot or support under it. It's being supported by the pillars given by P1 and P2. Now here in this case, we know the pull of gravity of the car, which is given by 2 times 10 to the power 4, and we know the pull of gravity of the bridge, which is given by 5 times 10 to the power 5. However, we have two unknowns given by Fp1 and Fp2. So we need another equation in order to solve for Fp1. And here we need to use the rotational equilibrium, but before we use the rotational equilibrium, we need to choose the pivot point. The pivot point is not specified in the exercise, then we're free to choose it as we like. Even more importantly, if it is under equilibrium, which means rotational equilibrium, as we said previously, and we can choose by that the pivot point anywhere along the system. Then here in this case, we have two best choices, or let me say 4. You can think about this one. You can think about this point, you can think about this point, and this point as well. And now let me tell you that the best choice would be this point. Why? Because upon choosing the pivot to be this point, the force Fp2 will be eliminated and we'll be only left with one unknown, which is Fp1. So even no need to use this equation from the beginning. Let me repeat and say here, the bridge is under rotational equilibrium. under equilibrium, which means rotational equilibrium, which means it is under rotational equilibrium for any pivot point along the system. We can choose, for example, at this point at the left end, at the right end, at this point, or at this point. By choosing at this point in particular, we would be eliminating FP2 and only determining FP1. However, now if we choose it along this point, we would be eliminating FP1 and we would be calculating FP2. Since our question is to calculate the left side pillar, then we're interested in FP1, then we're gonna choose the pivot point to be at this point. For this reason, I'm going to say choose the pivot to be at pillar 2. And now we're gonna say, so if the pivot is here, then that would be the radial direction, and that would be the tangential direction for FP2. That would be the tangential direction of FP1, and FP1 would be 16 meters away from the pivot, because if this is 4 and this is 4 and the total length of the bridge is 24, then the remaining length would be 24 minus 8, which is 16. Now let's determine the torque exerted by each of the three forces given by FP1, FGC and FGB. FP2 would produce no torque because the line of action of FP2, according to our choice, passes through the pivot. Now FP1 will cause along the pivot rotation in this direction, which means in the negative direction. FP1 lies along the tangential direction, so no need for a projection, and D1 would be the distance, which is 16 meters. Now here I also added the distance from the pull of gravity of the car to the pivot point, which is 12 meters. Now the torque produced by the pull of gravity of the car, now that would be the radial direction, that would be the tangential direction, no need for a cosine, and that would cause a torque in the positive direction. For this reason it's positive, and DC would be the distance from FGC to the pivot, which is 12 meters. And now, okay, this is the tangential direction, then FGB lies along the tangential direction, no need for a projection, and the distance would be given by 8 meters, then that would be plus FGB multiplied by dB. Now torque net would be equal to 0, that's rotational equilibrium, so that would be tau P1 plus tau GC plus tau GB would be equal to 0. Now we didn't include, I repeat again, tau of P2, simply because the line of action of FP2 passes through the pivot point. Now we replace all of these three expressions in this linear equation and we get this, and we need to isolate for FP1, then we move these to the other side. Now upon moving these to the other side, we would have minus FP1 D1, so let me say this is small p1 D1, which is equal to minus FGC DC minus FGB dB. The minus sign would cancel and we're left with FP1 multiplied by D1 equals FGC multiplied by DC plus FGB multiplied by dB, and we're isolating for FP1, then we take this down and it would be as follows. Now we can replace all the numerical values and we end up for FP1 given by 2.65 times 10 to the power 5 newtons, which is the value or the magnitude of the force FP1 along the pillar 1. Now if you're interested in determining in part B, calculate the force the right side pillar exerts on the bridge, we can do it in two ways, as you can anticipate. The first one is by referring to the first equation that we wrote down. Now we have only one unknown FP2 because FP1 is already determined. Then dragging this to the other side, that would be FGC plus FGB minus FP1, and we have all the values, we can plug them and we would get 2.55 times 10 to the power 5 newtons. So this is one suggested solution. Another healthy solution would be to consider again rotational equilibrium, but this time instead of being at P2 to eliminate P2, it would be at P1 to eliminate E1, and as anticipated the result should be 2.65 times 10 to the power 5. And by that, now our pivot point is chosen at the pillar 1, so we need to specify the torques of the three forces that we're interested in, P2, GB, GC, along the pivot, which is located to the left now. Now for the torque produced by the pull of gravity, that would cause the bridge to rotate in this direction, which means minus clockwise FGC DC, it lies along the tangential direction. Similarly for GB, and as for FP2, it would be in the positive direction and along the tangential direction. Replacing them in the rotational equilibrium equation, we would get Fp2 d2 minus Fgc dc minus Fgb db equals to 0, and we're isolating for Fp2. We take those to the other side, that would be positive, and we divide by d2. We would get the following fractional expression, replacing the values, and we would get 2.55 times 10 to the power 5 newtons, which is the same exact value that we have determined in the first method. Always remember that different methods should give you the same answer and not different answer. And now for the rest of the video, we're gonna solve some exercises. For the wheel and axle system shown above, which of the following expresses the condition required for the system to be in static equilibrium? Then static equilibrium means rotational equilibrium for sure, which means torque net would be equal to 0. Now here, what are the forces that are acting on the system? So here for sure we have the pull of gravity, we have the reaction, but we won't consider them because they will be passing through the pivot point, which is the center. So the only two forces that are acting on this wheel axle system is basically the force exerted due to the mass m1, which is along the tension. So here I'm gonna do it once. We have the pull of gravity down, Fg1, which is equal to the tension up. But if this string is massless and inextensible, so here we'd have a tension T1, which is equal to this tension, which is equal to the pull of gravity. So in brief, you can say that here we have the pull of gravity Fg1, and here we have the pull of gravity Fg2. So what is the torque produced due to this force? This will cause the system to rotate in this direction, which is positive, along the tangential direction. So here no need for a projection, because that would be the radial and that would be the tangential. That would be plus Fg1 multiplied by the distance d from the point of application of the force to the pivot, which is A. Now Fg1 would be m1 multiplied by g multiplied by A, and for the torque produced by the pull of gravity 2, so that will cause the system to rotate in this direction, which is negative, minus Fg2 multiplied by the outer radius, which is B, and that would be minus m2g multiplied by B. Now here, either we say tau1 plus tau2 is equal to 0, which means that m1ga minus m2gb equals to 0, which means m1ga is equal to m2gb, or similarly we can say that torques that are trying to rotate the system to the left should balance the torques that are trying to rotate the system to the right, which means that m1ga is equal to m2gb. So both equations are perfectly the same. G and G cancels. That would be A m1 is equal to B m2, which makes B to be the correct answer. Now a wheel of radius r is fixed to an axle of radius r over 3 and rotates at a constant angular speed omega. Now here, constant angular speed omega is exactly the same as we're saying that the velocity 0. Velocity 0 means no acceleration. So we have torque net would be equal to 0, then we are in rotational equilibrium. As shown in the figure above, a force of magnitude F1 is applied tangent to the outer edge of the wheel as shown here. So it's along the tangential direction and it's rotating in this direction. Then the torque it's producing is given by minus F1 multiplied by capital R. A second force of magnitude F2 is applied tangent to the edge of the axle to keep the wheel rotating at a constant angular speed, which means we're in rotational equilibrium. So this force would produce a torque given by F2 multiplied by R over 3 in the positive direction. So what would be the magnitude of F2? So we can directly say this torque should balance this torque, which means that F2 R over 3 should be equal to F1 multiplied by R, and we're searching for the value of F2. Now R would cancel, then F2 would be given by 3 F1, which makes D to be the correct answer. An experiment is performed by placing a known mass with its center of mass at a distance of 3 meters from the fulcrum as shown above. An unknown mass is used to balance the system with its distance from the equilibrium not completely measurable. Every time the known mass is changed, the unknown mass is moved until equilibrium is reached. The data that were gathered for this experiment are below. So here what they're doing is the following. So we have a known mass. Each time we change a known mass, the same unknown mass is, so we're not changing the unknown mass. The unknown mass is the same to be capital M. We're changing only the known mass from 75 to 85. Each time we change the known mass, it means that we need to change the torque in order to balance the system. So the first time it's X, the second time is X plus 1. If the mass of the beam is ignored, so there will be no force due to the mass of the beam. Now, what are the hidden forces that are acting on the system? We have the pull of gravity due to the known mass. We have the pull of gravity due to the unknown mass. We have the pull of gravity due to the beam, and we have the reaction, which is arbitrarily chosen. We will ignore the one for the reaction because it passes through the fulcrum or the pivot, and we're gonna ignore the pull of gravity of the beam because it's massless. The value of the unknown mass is most nearly equal to which of the following. So here basically we have two unknowns, the capital M and the capital X, which represents the location, which is the distance in meters. Then we have two unknowns. We need to set up two equations in order to solve for the system. This pull of gravity produces a positive torque. This pull of gravity produces a negative torque, and they should balance each other. Now, what is the torque that it's producing? It's due to the pull of gravity, which is 75, the first one, multiplied by 10, multiplied by 3. That should balance the pull of gravity, which is M multiplied by 10, multiplied by the distance X. So the first equation is given by 225, should be equal to, sorry, let me do it the following way. 10 with 10 would cancel. That would be 225 is equal to mx. So that's the first equation. Now the second equation would be the mass, which is 85 multiplied by 10. We didn't change the location of the known mass, multiplied by 3. That would be equal, we didn't change now the unknown mass, multiplied by 10 to produce force, multiplied by x plus 1. So this equation becomes, if we cancel 10 with 10, that would be 275 equals m into x plus 1. Now here we have two equations, equation 1, equation 2, and we need to solve for m and x, but in particular they are interested only in the value of m. So there are several ways to solve them. Since m appears on the right hand side in both members, then we can divide equation 2 by equation 1, and here we would get 275 divided by 225 is given by m into x plus 1 divided by mx. In this case, m with m cancels. 275 divided by 225, or we can do it the other way around, we cross multiply, then 275 multiplied by x is equal to 225 multiplied by x plus 1. Then now we can expand. And we can move this to the other side. That would be 50x is equal to 225, which means in this case capital X would be equal to 7.5 and the unit of x would be meters. But notice that we're not interested in determining the value of x, we need the value of m. But now we can refer to this equation. M is given by 225 divided by x, which is 7.5. Plugging that expression on the calculator, we will get that the mass is given by 30 kg, which makes C to be the correct answer. And finally, exercise 4 as an exit ticket for today's video. A system of two wheels fixed to each other is free to rotate about a frictionless axis through the common center of the wheels and perpendicular to the page. Four forces are exerted tangentially. Tangentially means the torque would be just force times the distance. In this case, the distance from the pivot, which is the center of the disc, is the radius, to the rims of the wheels as shown above. The magnitude of the net torque on the system about the axis is given by, so they want the magnitude. We're not interested whether the positive direction would be counterclockwise or clockwise. We just need to fix a direction. Then in this case, let's produce the torque. Let's calculate the torque produced by each force. So let me start by this force. Let me eliminate it. That would produce a torque in the positive direction. So the torque 1 would be given by F multiplied by the outer radius, which is 3R. Now the torque 2 produced by this force, that would be also positive, multiplied by the inner radius, which is the double of R. Now this torque, which is also F multiplied by 3R, and we're left with the torque 4, which is given by a negative, the double of F multiplied by the outer radius. Now here what do we have? We have 3 plus 2 plus 3. So 6 plus 2, that would be 8. 8 minus 6, that would be 2. Or you can do it in the following way: 3FR plus 2FR plus 3FR minus 6FR, which is basically the double of FR, making C to be the correct answer. Then that's it for me in this video, guys. See you soon in a new one.